I agree with you. And what do we have left? Is it easy enough to teach yourself? I'm not quite sure about that, so we're going to try to get through it all. You looked at it. You didn't turn it in. All right. On this reaction coordinate diagram, where we were yesterday, we're looking at EAS reactions. Can someone just reiterate? How does an EAS reaction differ from an NAS reaction? Good. Here, benzene is the nucleophile instead of the electrophile. I wanted to point out, did you notice how we had 6 different named reactions for EAS? Bromination, chlorination, alkylation, acylation, sulfonation, nitration. Do you know how many of the NAS reactions were named? They weren't named. We recognize that it's usually nitrogen or it's oxygen as the nucleophile, but they didn't have a name. We didn't call it nitrogenation and oxygenation. We just said it's NAS and these are the nucleophiles that you'll have. But with EAS, we're like, by the way, depending on what the electrophile is, here are all of the different things. I don't necessarily have a good answer for why that is, but I suspect it's because the mechanism for NAS is identical regardless of what the nucleophile is. But EAS, the mechanism is slightly different depending on what the electrophile is. So we were saying if benzene goes through aromatic substitution, here's our starting material. Here is our sigma complex. I have to go up in energy to break aromaticity. That's not an easy thing to do. And once I get my sigma complex, resonance stabilized, then I can do elimination. Addition, sigma complex, elimination. So let's say that this is for benzene. I had started drawing this yesterday. I do apologize. My colors will probably be different than what they were yesterday. But we said that electron withdrawing groups activate the ring. That means instead of needing to go so high in energy, I actually come down in energy. I get a lower energy intermediate, and then I go to my product. So this is electron withdrawing group. But let's say that this intermediate is the meta intermediate. What do I mean by that? I've got my electron withdrawing group. Oh man, shoot, I'm sorry. I hope you didn't listen to anything I said. Electron donating groups activate EAS. Were you confused at all? If you were, that's a good thing. If you weren't, it's okay. Electron donating group donates, activates the ring, decreases that activation barrier. In this meta intermediate, it means the electron withdrawing group and the new electrophile are meta to each other. And here's the deal. The electron donating group is never able to engage in resonance. The electron donating group does make it a better nucleophile, but it doesn't actually stabilize the intermediate more. If my electron donating group can be placed ortho or para, and here's what I'm going to draw. I'm going to show that the electron donating group can actually come in and take part in that stabilization. It can engage in the resonance, and it can provide extra stability. So that drops the energy even more. Relative to benzene, electron donating groups activate the ring. Who was asking me about activation at the end of last class? Those were some good questions. Can't remember. Why does it activate the ring? takes less energy to react. So now it's going to happen even faster. Okay. If you slap an electron withdrawing group onto the ring, relative to benzene, this is going to increase the reactivity of the ring. But if the electron withdrawing group is meta to that new electrophile group, we see a lower energy activation compared to when that electron withdrawing group is ortho or para. And the reason for that, I don't have enough space there. Let's not get into all the resonance forms. I've done it before. Usually it just kills time. The reason for that is when the electron withdrawing group is ortho or para to the new electrophile group, we end up putting this positive charge right next to the group that is already pulling electrons away. It's like taking two ends of a magnet that are the same and trying to push them together. It's very high energy. You get this bad repulsive force. Electron withdrawing groups do not stabilize the intermediate of EAS. They destabilize the intermediate. Relative to benzene, they are deactivators. But they deactivate even more if that group is placed orthopara. Where do halogens fall in here? Yeah, relative to blue, halogens fall in. They're not as strong of deactivators as are nitros, sulfonyls, cyanos, but they are deactivators. And yet even still, we could say halogens with a meta-directed new substituent or an orthopara-directed. Which one does halogen prefer? Look at your notes. Orthopara. So we're learning two things. Electron withdrawing groups make it harder for the ring to do this. And out of the two options, they would prefer a meta substitution. Electron donating groups make it easier for the ring to do this. And out of the two options, they prefer orthopara. Halogens live right in the middle of those two groups. Halogens make it harder for the ring to do it, but make it easier at the orthopara. Halogens are not electron withdrawing groups, and they're not electron donating groups. They're actually both. They pull electron density away like electron withdrawing, but they stabilize the intermediate like electron donating. It's not one or the other. They're technically both. You guys all right with that? I want you to think about those three types of groups because that's what we're going to be dealing with. So let's do some examples with direction, because after that we're gonna get into mechanisms. Okay, there's something I don't think I've ever said in class before because I always forget to. There are some electron withdrawing groups that deactivate the ring so much for specific EAS reactions that those reactions don't happen. So for instance, alkylation and acylation, putting on a carbon group, putting on a carbonyl group, they don't happen with just electron withdrawing groups on the benzene. I try to avoid situations where I give those to you, but sometimes I mess up, in which case you just kind of work through the patterns of how these groups direct, and you just make predictions about what would form. But I do my best to make sure you don't get those situations. So I want to start with a comparison. Let's start with phenol. Versus nitrobenzene. And let's do bromination on both of them. Can I change that from nitro? Can I make it sulfonyl? Sulfonyl benzene. Thank you. In terms of substituent type, these are all the same. Let's add one more to the comparison. And let's add bromobenzene going through bromination. How is the OH group identified as a substituent? Is it electron donating, electron withdrawing, or halogen? Electron donating. What is it about the oxygen that makes it electron donating? It's the lone pair. Actually, identifying that it's electron with electronegative might make you think it should be electron withdrawing. Doesn't it pull electrons towards itself? Yes, it can, but it also has these lone pairs that would like to be in resonance with the ring, because resonance is always a stabilizing force. So by making a lone pair in resonance, conjugated, it actually stabilizes it. Electron donating, sulfonyl. Electron withdrawing, halogen. Which of these bromination reactions will proceed the fastest? Phenol. Hydroxybenzene. Fastest. Because it is the most activated. Which of these will occur the slowest? The sulfonyl. So how are you supposed to know whether sulfonyl or bromine is slower? Halogens are right in the middle of electron donating and electron withdrawing groups. They don't deactivate as much as electron withdrawing, but they certainly aren't electron donating. Okay.
I'm just a little behind. I'm getting it.
Okay. Benzene is no longer the main part of this reaction. Phenol is the part of this reaction, which means the oxygen is going to impact how the benzene ring reacts. There are three positions relative to that oxygen: ortho to it, meta to it, and para to it. How will the oxygen activate the ring? Will it activate the ring ortho and para? Or will it activate the ring meta? Ortho and para. So I can expect two major products. Ortho-bromo-phenol and para-bromo-phenol. I have a question for you. If I'm asking you to do a synthesis, and it's obvious that you need to brominate phenol, but you don't want both of those products, you just want one, how do you go about that? If you're in a lab, you can actually separate these two structural isomers. They have different properties, so it's very likely that they will pass through column chromatography differently, and you can isolate one from the other. So if you're doing this in a real lab, you make both, you can't really control it, you get the one that you want, do whatever you want with the other. On paper, you predict this reaction. You don't have to say that both form, you just use the one that is relevant to your synthesis. Is that fair? If two things can form in a reaction and one is useful to your synthesis, then just show that one. Ignore the other one, which in a lab you could isolate. and throw away. Okay, when I brominate sulfonyl benzene, how many products do I get? Just one, where it's meta-substituted to the sulfonyl. How many meta positions? Which one should I choose? Either. This is an achiral molecule. Those two meta positions are identical to each other. They're not different. So it does not matter where you draw this bromine. You flip this molecule like a pancake, it's the same molecule. How does bromine direct the bromination? Orthopara. Is that what you said?
Yeah.
OP. Orthopara. So just like phenol, I get two products, ortho-dibromobenzene and para-dibromobenzene. Brilliant. Yeah, Lily.
Wait, sorry, how do we know that it's going to be orthopara?
We'll actually look at the mechanisms,
Okay.
and we'll look at how bromines stabilize the intermediate if and only if the new group is being attacked orthopara to itself. That's why it's an orthopara director, is because it stabilizes the intermediate at that orthopara position. Good question. What else? Milena.
So, this is a specific question, but when we are presented with a reaction, like with the reagents and everything, like we should be able to immediately identify, I guess because we've named them, I guess, but this is an EAS reaction, therefore I compare it with what? Right?
Love it. How do you distinguish between EAS and NAS? What do you guys think? What's the difference between EAS and NAS based on the reagents?
EAS or NAS.
Yeah.
So I don't know if this is like completely like always the case, but I've noticed that with like some of the like the NAS equations, right?
Mm-hmm.
Like it actually shows kind of like a substitution of like one kind of like a substituent to the other. Right? EAS, it's almost kind of like a fill in the blank kind of thing. Like,
And that's because we assume the hydrogens on the benzene ring. NAS, a bromine or a chlorine has to get substituted. That's one way that you can identify that it's NAS. A substituent gets substituted. Whereas EAS, you said it seems like a fill in the blank.
yeah, like you kind of
Take this position and just put something there.
yeah,
We are substituting something.
yeah, but it's like
It's the hydrogen that we assume. There's a hydrogen there. It has to be substituted. If hydrogen is substituted, EAS. If halogen is substituted, NAS. There's another way that we can think about it too. Peyton.
I think about it like electrophiles give and nucleophiles take. So like if the reagent is giving you something, then it would be EAS. But like if it was the opposite.
You're actually flipped on that.
Okay.
Nucleophiles give. Nucleophiles have electrons that are used to form bonds to electrophiles. Electrophiles accept electrons from a nucleophile.
Yes.
So if your reagent is negatively charged, that's a nucleophile, and that reagent is going to attack your ring, NAS. If your reagent is not negatively charged, and if it can, in fact, form a positive charge, then it will be attacked by the ring, EAS. So I like that idea. Think about what your reagent can do. Can your reagent attack? Does it have a negative charge? Nucleophilic aromatic substitution.
Like if we see a salt or sodium,
Yeah, if you see sodium, potassium, those are good indications of an anion nucleophile. The sodium is just balancing the charge for your nucleophile. The potassium is telling you that the other reagent has a negative charge. Elliot?
The like nucleophilic attack piece makes sense, but haven't we like one takes the electrons, becomes a nucleophile,
Mm.
and then attacks.
Mm-hmm.
So like,
But Br2 itself does not split into Br minus and Br plus. What we saw was alkenes will form a halonium ring with one of the bromines, which is actually, and I don't tell you this in OChem 1 because I think it's stupid. That reaction is called electrophilic alkene addition. You're adding to an alkene an electrophile. But that's not really true because the alkene attacks bromine, okay, electrophile, at the same time that bromine attacks the alkene, nucleophile. So what role does bromine have? Both. The bromine is attacking as a nucleophile and being attacked as an electrophile. That's not electrophilic addition. In that step, the Br minus gets kicked off. Not because Br plus is formed, but because a Br plus ring is formed. And then that Br minus does act as a nucleophile in the next step. So if anything, it feels more like nucleophilic alkene addition, but they label it as electrophilic. All right, here's the deal. I want us to do a little bit more practice. We're going to take the products that we formed, and we're going to do some more predictions. So I want you to take this para-substituted product, and I would like you to give me a reagent that produces this compound. I'd like you to predict what could form from this second reaction. And I have a hint that I can fill in a little bit. And then down here with this second one. What do I want to have you do? I think I'll have you do this. Predict the product again. This is the time to ask questions, so if you're not sure where to start, if you're not sure what you're looking at, that's what I'm here for. Oh, I'll give you that hint if you want. They're all EAS right now.
Okay.
This took it up a level, right? Because now you have two substituents, not just one. Very nice. Good start.
Last time, like after worksheet 2, I just want might as well get good at drawing.
Yeah. Missing one thing here. Catalyst.
yeah.
This is EAS, but you've treated it as if it's NAS. NAS would substitute the bromine because a nucleophile would attack that carbon and then the bromine would get kicked off after. Right. EAS means something's going to happen with one of these available positions. Let me help.
I feel so bad. Ella's been asking me questions all day, and I'm just like, yeah, this is how you do it. And she's like, but why? And I'm like, I don't know.
Well, it's
I'm
not
like,
just
I'm
all
like the
day, it's every
worst.
class. You should ask me those questions.
No, it was because we were trying to do the written work, and I was like,
Oh, yeah.
I'm so lost.
Yeah, yeah.
'Cause we
Okay,
haven't done any of the
I'll be right
written
there, Sarah.
Well, so we're adding a methyl group,
Great.
but then, like, how do we know that, like, we need, like, the chlorine?
So let's look at all of our reactions.
Yeah.
We're adding a methyl. What does that agree with the most here? Which of these?
This one?
Alkylation. Great. So in our example, we had tert butyl chloride and we got tert butyl benzene.
Okay.
So whatever group I want, connect that to a chlorine
Okay.
and you are going to get
Can
what
it
you need.
be any halide?
Yeah, I can.
Okay.
But for simplicity's
Mainly
sake,
that one?
for simplicity's sake, we'll use alkyl chlorides.
Okay.
But it also needs a catalyst. Brilliant.
Okay.
Without that catalyst, it's not going to proceed. What you got, Sarah?
I have a quick question.
Yeah.
So, you know how these are orthopara, so there's two options?
Yeah.
How do you know that this isn't orthopara? No, let me ask more.
Great question. You already labeled this as electron withdrawing group. The sulfonyl is an electron withdrawing group. And did you get yesterday, last class's lecture?
They sent me the notes.
Okay.
Yeah.
We learned that electron withdrawing groups
Okay.
are meta-directors.
Okay.
Halogens and donating groups are orthopara. Electron withdrawing groups are meta. And actually this graph that you copied down tells us why. Why does the electron withdrawing group prefer a meta substituted product over orthopara? The orthopara intermediate is much higher in energy, and the meta substituted intermediate is lower in energy. So what's more likely to happen? The meta. And why is it more stable? Why is it more likely to happen? Lower energy, and it's actually because of where that charge gets placed if the electrophile is meta versus if it's para. This is a bad placement of that intermediate charge. This is a less bad placement. Still bad. Okay, and then the other connection I wanted to point out was these are deactivators. This is an activator, which is why halogens make their own group. They share properties with donators, orthopara. They share properties with with withdrawers, deactivators.
Okay, so metas always have one,
Yeah. Yep.
and then orthopara.
Good. Because an ortho position is different than a para position.
And then halogen can have both.
Halogen will do orthopara. Donator will do orthopara.
Quick question.
Yeah.
It's just a verification. So if you substitute with halogen, it's NAS?
Yep.
Okay, I just kept mixing up NAS, EAS.
You got it.
Sure I got it down right. Would that,
We want to use one of our reactions from
I'm good right?
from that little diagram of benzene to 6 different reactions.
That's this.
Oh, good,
it's
good,
just
good.
easier to list.
Absolutely. Well, this actually I think is from our last section.
Is it? Sorry, I've been kind of scattered.
No, that's okay. I think it will be, I think it's this.
It might be.
Friedel-Crafts alkylation. If I want to add an alkyl group, which is what you did. Oh, where'd it go? Oh, thanks. I want to add an alkyl group. And you recognized I'll have CH3 something. We actually want it to be CH3Cl, not OH.
Okay.
The Cl and the AlCl3, that's our catalyst. That will give us a alkyl group. So you recognized what you want the group to look like, so just provide it with Cl.
Okay.
Instead of OH. We'll do the mechanism later and it'll kind of show why OH won't do it, but Cl will.
So because we already established that this is a meta, it has to go on the only
We're just
remaining
wondering
meta.
if the reasoning here
Okay, thank you.
works.
Strong.
Beautiful. okay.
Perfect. Well done.
Does this work?
Yeah, it does. I'll take it. You won't see it from me, but I will take it from you.
So I was wondering about this one.
Great.
And
It's
then
perfect.
for this one, I just said that I figured this one wins the tug of war.
Ah,
Like it's ortho and para probably two are deactivated, so I just drew this, but I'm not sure.
okay. So you put it on the second meta position.
Yeah.
What we have to decide is, does bromine deactivate the ring as much as sulfonyl? Which of them is going to have a higher activation barrier? Remember how we said halogens are in the middle between electron withdrawing and electron donating? That means the halogen is a deactivator, but not as much of a deactivator as the electron withdrawing groups.
Yeah.
So actually, the halogen has a stronger impact on where the next group goes. Mm-hmm.
Okay.
So we say, yes, these are both deactivators, but this is less of a deactivator. So it will decide where the thing goes.
Okay.
It will stabilize the intermediate the most. This will not stabilize the intermediate.
Okay.
So does that change your answer? This one's great, by the way.
Think about it.
Okay. Can we go through them? I want to point out a lot of you got this first one right away. You saw that methyl group. You saw it as alkylation. And to alkylate, I just need that same group again, plus a halogen, and it'll be often shown to you as a halide. Sorry, as a chloride. But we also need the catalyst. Without the catalyst, this reaction takes a lot of energy. Great job. Now the second one, we have to consider that the sulfonyl group will try to direct this new bromine meta to itself. And by try, I mean the lowest energy option is if the sulfonyl group has the new bromine meta to itself. But the bromine will try to direct it ortho and para to itself. So we have to ask ourselves the question, which group controls the directing? The best answer here is, what do you want to, huh?
No, I'm just thinking to myself.
The best answer here is whatever lowers the activation barrier the most controls the directing effect. And I gave you electron withdrawing groups, I gave you electron donating groups, and I told you to think about halogens. So let's actually draw the halogens. Here's the halogens, and of course, remember, halogens prefer ortho-para placement. If the sulfonyl group directs the new group meta to itself, that will still increase the energy more than if the bromine directs the new group ortho-para to itself. Why is it better for bromine to direct? It's less of a deactivator, which makes it more of an activator, because it stabilizes the intermediate. So bromine is my best activator. It's like looking at -10 and -5 and saying -5 is the most positive number. It's not most positive. It's more positive than -10. Bromine is a better activator than sulfonyl. How do we keep track of that? The halogens are right in the middle. Electron donors, best activators. Electron withdrawers, worst activators. Halogen, actually pretty close to the aromatic ring. It's fairly close to the bromine. All right, that means I actually get two products on this reaction. One where the new bromine is ortho to the original bromine, and one where the new bromine is para to the original bromine. Do you notice how neither products have it meta to the sulfonyl? But doesn't the sulfonyl want it meta to itself? No, honestly, the sulfonyl doesn't want it at all. The sulfonyl is trying to stop this reaction from happening. But the halogen can help enable it.
I was gonna Because technically, isn't there two?
Oh, there's, oh,
ortho
yeah.
positions? Okay.
Thank you. I didn't notice that. So, third product. You know, I used to ask questions about which of all of these three possible products is the most likely and the least likely. I stopped getting away from that. I started getting away from that because there are some situations where even a more sterically strained product is more likely than a less sterically strained product at the wrong position. And that just gets a little too confusing. It's already hard enough to predict where these go. Let's have that same discussion here. Which bromine is the better activator? Which one is the director? Yeah, either of them can be. And it really doesn't matter. So whichever position, or whichever bromine is directing, there's only an ortho position available. So this will give me 1, 2, 5 tribromobenzene. Oh, you know what? I was just really on a benzene drive. Oh, you want benzaldehyde. By the way, this is a time I'd like to remind you of what carbonyl groups you can acylate. Ketones and aldehydes. The acyl product that you'll get, the carbonyl product you'll get, ketone or aldehyde. You will not acylate a carboxylic acid or an amide or an ester. Deal? You will not do that. So any synthesis where you need to end up with a carboxylic acid, you're going to have to do that by some other reaction. You won't do that by acylation. Lily?
So even if, going back to the second one we did, so even if it's meta, it's always going to try to be ortho and para because that's better?
You're talking about this one?
Yeah.
Even if meta is an option,
Yeah.
the bromine is not directing meta. The bromine is directing ortho-para. And that will be the lowest energy pathway. To get the meta-substituted product, it's going to have to go to a higher energy, and it's not likely to do that.
Okay.
Even if the ortho product has a lot of steric strain, it's still more likely. But that's beyond what you're going to have to do. Can you name that last compound, the one with the aldehyde? I can say it different. You can name that last compound. Perfect. How'd you start that, Milena?
Basically, I just did the aldehyde group as number 1 and the lowest locum set.
I know how to name the bromines on benzene. Bromobenzene. Easy. How do I name the aldehyde on benzene? Benzaldehyde. It's not a common name. Honestly, it might be its common name, but that's the name that we use. Benzaldehyde. Well, I don't have another way to name it, that aldehyde, so I'm going to name the whole structure benzaldehyde, and I'll name the bromines as substituents to that. And I want the lowest locant set, so I'll number in a specific way that minimizes my locant set. 2,5-dibromo. Because I named it benzaldehyde carbon has to be carbon number 1. Because I actually could see some of you thinking, can I get a lower locant set if I go 1, 2, 3, 4, and I get 1,4-dibromo benzaldehyde? Yes, you can, but by calling it benzaldehyde, you have already assumed that this is position 1. Great job, guys. let's look at mechanisms. Haha. Okay. I gave you guys a worksheet last week. Nope, sorry. I gave you guys a worksheet on Tuesday that has some mechanisms on the back, but I'll be honest, they're not mechanisms on the back. They're just reactions that we're going to go through to practice our mechanisms, okay? Out of the 6 EAS reactions, I am asking you guys 4. And I want to remind you that this is essentially 2 sets of 2. And I only have 1 worksheet left. But this is on Canvas, so does somebody want the physical one? It's the one that started with the hexagon, and then it has mechanisms on the back. You want the physical one? And you can download it from Canvas too. Also, I have another worksheet that is on Canvas. This is one we're not going to do, but it's practice problems. Did I give that to you yet? No. Okay. All right, the first problem on our mechanisms. What type of EAS are we doing? Did I give this to you? I give it to you.
Oh, this is different?
Yeah, that's not, the one I'm handing out right now is not the one we're going over. It's a bunch of practice problems that you guys will be able to do. I gave you one. Okay, the first one on our mechanisms sheet is what? Bromination. You want one? Oh, I'm sorry. You came in later than normal. I think that's why I thought I gave it to you already. What are we brominating? Benzene. Step 1. Activation of electrophile. I do not have an electrophile. I don't have a good electrophile right now. My catalyst will help me get a better electrophile. I'm going to draw benzene, but it's not going to play a role in this step. Instead, my electrophile and my catalyst will react. One of bromine's atoms donates a lone pair to iron. Iron is a Lewis acid. Iron accepts electrons. I get benzene, plus I get this iron complex. There's 2 different ways you can show this iron complex. Some people like to show it with all of those bromines explicitly shown. Some people like to just keep it as FeBr3. Since Br has accepted electrons, negative charge. Since bromine has shared electrons, positive charge. And I know you're probably thinking that you have identified the electrophilic bromine because there's a positive charge. But I'm going to psych you out. Step 2, nucleophilic attack. This is where we break aromaticity. Ooh, if I have to break aromaticity, can I draw my aromatic ring with a circle? No. Why not? Am I showing, if I draw out a circle and then I have that circle attacking, 6 electrons are attacking? Remember, there was a problem with the circle in the first place, and that is, it's a bad assumption. All right, I'm going to draw my, my iron catalyst with the bromines explicitly shown, because I want to remind you that there's a lot of steric strain going on right next to that iron. And this will help us understand why the ring attacks the bromine that it does. Is there a specific pi bond I need to start from? No. I don't have any other substituent that I'm going ortho, meta, or para to, so it does not matter which pi bond I use. All right, pi bond here attacks the outermost bromine. Why would it not just attack the bromine with the positive charge? Attacking a bromine with a positive charge wouldn't actually help that bromine out. What that bromine wants, it wants a bond back. So we attack the outermost bromine and break the Br-Br bond back to the positively charged bromine. It does not matter which of those two carbons I say did the attacking, which means it does not matter which of those two carbons I say lost the electrons. So I'm going to show that this carbon attacked bromine and this carbon took the electron, lost the electrons, takes the positive charge. Here's the deal. I am not going to leave it like that. I'm going to explicitly show the hydrogen that's on that same carbon. And I'm going to do this for two reasons. It's not for me. What? It's going to have to come off eventually. So that's a good reminder. I need that hydrogen to leave, so I'm going to draw it in. The second reason I'm going to encourage you to draw it, sorry, thinking. That's an sp3 hybridized carbon. That carbon will never be involved in the resonance forms in this sigma complex. So by drawing explicitly that you have Br and H means that you won't try to put a positive charge on that carbon. Okay, and my other thing here, FeBr4 minus. Step 2 goes on. This is not the end of step 2. All I have done here is shown one of my resonance forms. There's another and a third. In the first resonance form, the adjacent pi bond moves to the carbocation, leaving in its wake a new carbocation. By the way, this second resonance form is my favorite when it's got those parallel lines. I just like drawing the aromatic rings with the parallel lines. The third resonance form, the next pi bond moves to the carbocation, leaving in its wake a third carbocation. Step 3, elimination. This is where your catalyst comes back. Where's my protein shake? Sarah, you're trying to steal my protein shake. Okay, if I need to reform my catalyst, I'm going to have to break off a bromine. So in this step, I will need to show at least one bromine iron bond. Do you know I used to say, and I've said this even to you guys this semester, I've said that you need to show relevant lone pairs of electrons like this. There's 6 lone pairs on Br2. Only one of them is relevant to this mechanism step. But if you have a negative charge, you don't have to show the lone pairs. You can show the arrow coming from the negative charge instead. That doesn't apply here. Iron has the negative charge, but iron will not be using the electrons. I need this iron-bromine bond to break, so I will not start my arrow from the negative charge. I will start my arrow from the iron-bromine bond. Those are bromine's electrons. So bromine uses the electrons to bond to hydrogen. Elimination. Do you remember that from OCHEM 1? Beta hydrogen elimination. When a CH bond breaks, which way does it go? To the carbocation. To the carbon. Which means that carbon will take it to the carbocation. Hey, look at what I just did. I just reformed aromaticity, which means I can draw a circle again. I'm actually going to add something. You know, I called this elimination, catalyst reforms. I actually should have said catalyst and aromaticity reform. It's the elimination step that lets my aromatic ring return. That's important, isn't it? If I don't have aromaticity, I have just gone way higher in energy. And the whole point of this aromatic substitution is that I stay at a low energy structure. So I need to get back to aromaticity. Questions on this mechanism? Sarah? Oh, you know what? I do. Yeah. Thank you for bringing that up. HBr formed as our byproduct in that step. I'll be honest, if I'm grading a mechanism, I'm probably looking more for the final product being right, or you've already seen the final product. I look a lot more, though, for like these byproducts that form during the mechanism, because a lot of times those byproducts come back to become useful again. How many steps? 3 steps. It was not a lot of steps. One of the steps formed a resonance stabilized intermediate. Let me ask you this. Which of these 3 resonance forms is the most stable? I think you already said it. None of them. None of them are the most stable. They're all equally stable. They're all secondary allylic carbocations. Do you agree? They're all secondary carbons, and they're all conjugated. So these are all equally stable. Now, when I give you guys mechanisms, I'm not going to have you draw from benzene. You will be drawing from a substituted benzene, which means there will be one resonance form that is more stable than the others. So when we get into these other mechanisms, I'm going to draw the most stable intermediate rather than all possible intermediates. Here, all possible intermediates are the most stable. Okay, I have a second question for you. Should I have drawn the resonance forms when the sigma complex formed? Or should I have drawn the resonance forms down here before the elimination step? It doesn't matter, does it? Because if you don't want to draw your mechanism stepwise, then your mechanism might look like this. Activation of electrophile, nucleophilic attack. How am I going to do that? Elimination. It's all continuous. There is no right time or wrong time to draw the resonance forms. Anytime you have a resonance stabilized intermediate, all resonance forms exist at the same time. Okay, do you guys want to see the next mechanism and then take a break, or take a break and then see the next mechanism? Let's do the next one quick. What is the next reaction type that we're doing? Chlorination. Will this be similar or different from the halogenation mechanism? Similar. What type of substituent is already on my ring? Oh, I screwed up, huh? Yeah, when I gave you the structure. God, you could pay me $1 million, I wouldn't do it right. Because I only have the chlorine. Doesn't that look like NaS? God. Okay, sorry, you're supposed to have that same substituent. And then let's draw it para. There are two products, ortho and para, that form. We're going to focus on the mechanism for the para substituted product. Okay, there's that same substituent. Well, what functional group is that? Esters and ethers are very similar. Esters and ethers are both oxygens with carbon on either side. So how do you distinguish the ester from the ether? Ester has a carbonyl group and the ether has no carbonyl group. And they had to name them so similarly, like with 90% of the same letters. Ester. Is this an electron donating group, a halogen, or an electron withdrawing group? It's electron withdrawing? Electron donating? What evidence do you have? That is true that oxygen is electronegative, but the oxygen also has a lone pair. What evidence do you have, Max?
Just a lone pair on the closest oxygen.
Lone pair on the closest oxygen. There's another piece of evidence. The product is a para-substituted product. And that's clearly not a halogen, so it must be an electron donating group. Didn't we say that carbonyls are electron withdrawing groups? The carbonyl is not connected to the ring. The oxygen of the ester is connected to the ring. So this is not a carbonyl electron withdrawing group. This is an oxygen electron withdrawing group. Remember that we said as long as it's OR, it will be an electron donating group because the oxygen has a lone pair. All right, well, R in this case just happens to be a carbonyl, but the carbonyl is not connected to the ring. Great. Step 1, activation of electrophile. Once again, I'm going to draw my aromatic ring here, but it's not going to play a role because this first step is just chlorine and the catalyst. What do you suspect is going to happen? Make a comparison to something you already know. Yoon, what do you think? Yeah, just like bromine formed a bond with iron, chlorine forms a bond with aluminum. I didn't have a great electrophile before, but now I do. Now I have an electrophile that really wants to accept electrons. Step 2, nucleophilic attack, which means no more ring, no more circle. You know, I don't want to throw a wrench in your understanding here, but you can abbreviate that ester group as OAC. You guys may have seen acetic acid represented as ACOH. This is an acetyl group, but I'm not going to encourage it. Does it matter which of my pi bonds is used in the nucleophilic attack? Yes. Because I want my chlorine to end up at a specific carbon. So I need to use electrons from that specific carbon. Now, to be fair, I know a lot of you, as my students, are just copying down the placement that I've drawn my pi bonds, but it doesn't really matter where you've drawn your pi bonds. This carbon will always have one pi bond connected to it. That pi bond needs to attack. This carbon is going to be the one that attacks the chlorine, which means that this carbon's pi bond needs to be the one that attacks. Before I start there, though, is oxygen activating that carbon, or is oxygen not playing a role yet? No? I think oxygen is activating that carbon, and I'm going to show it to you. Instead of having you form all possible resonance forms, I'm going to show you how to form the major resonance form because of the activation of the oxygen. This oxygen is orthopara directing, which means that it's going to help force that para position to attack. Oxygen donates its lone pair to form a double bond. That's going to break the octet of the carbon in the ring. So the pi bond in the ring now needs to move. The pi bond in the ring moves over. There's only one way that it can move. This carbon needs to lose the electrons, so the pi bond in the ring shifts to the other carbon that has the pi bond. Okay, that's going to cause another problem because this carbon is now going to have too many electrons. So now this pi bond needs to break. Wait, didn't you all say that's the pi bond that needed to break in the first place? Because it's this carbon that attacks the chlorine. I'm going to say it a different way. Why is it the para carbon attacks the chlorine? It's because oxygen is activating the ring with extra electrons that end up going to that carbon. Milena.
We also say that, like in this case, we are getting the pair product, but
Yep.
we also have the second arrow that we use for the position attack, right?
We could have gotten an ortho position, which means that this carbon, ortho, this carbon could have attacked. That would have been shown by this pi bond attacking from that carbon. We could have shown it directly. And we are still showing it directly. Here's what I'm trying to teach you. We could have started with just this pi bond breaking, and then putting a positive charge next to it, moving that positive charge, and then showing the oxygen stabilize the positive charge. There's no reason we have to do all of that work. Oxygen is stabilizing the positive charge immediately. Oxygen is forcing the positive charge to form. Oxygen is pushing electrons through. All right, let's show what this looks like, because I know this is going to feel a little confusing. First of all, para carbon now has the chlorine, and I'm going to show that hydrogen just like last time. My oxygen has just formed a double bond. Yeah, Lily, before I get too far.
I was just wondering, in between step 1 and 2,
Yeah.
with the aluminum group, why did the charges switch between the chlorine and the aluminum?
Oh, I'm glad you noticed that. What do you guys think? I just messed up. What's the right answer? Is it this or that? Bottom or top? Bottom is correct. It matches what we had with our bromines. Thanks for pointing that out. Aluminum should have had that negative charge. Chlorine has the positive. Oxygen has just formed a double bond, correct? Okay, here's that double bond. Did anything happen to this pi bond in the ring? No, so that pi bond is still there. Did something happen to this pi bond in the ring? Yeah, it shifted over, so that pi bond is here. I also changed this. I now have AlCl4 with what charge? Negative charge, just like the FeBr4. Okay, somebody help me. I just went from net neutral, neutral, positive, negative, neutral, to net negative. Oxygen has a positive charge. How do you know oxygen has a positive charge? Has 3 bonds. It donated its lone pair. When an atom donates a lone pair, it takes on that positive charge. So oxygen here with 3 bonds has a positive charge. There are 3 other resonance forms. They look like this. They just have the positive charge sitting on the carbon. So I want to ask you this. Out of the 4 total resonance forms, 3 where the positive charge is sitting on carbon, and 1 where the positive charge is sitting on oxygen, which is the major resonance form? Why? This is why it is an orthopara-directing molecule, because it can take the oxygen. But why is it better to put a positive charge on oxygen than carbon? Electronegativity would seem to disagree. This is more electronegative. It should take a negative. This is more electropositive. It should take a positive. The octet rule. Do you remember our rules for resonance? Number 1, minimize charge. Number 2, maximize octet. Broken octet, 6 electrons. 6 electrons. 6 electrons still has 8 electrons. And if you don't believe me, that's because I forget to draw in all of my lone pairs. That still has a lone pair on it. 6 electrons. 8 electrons. Maximized octet. Then we start to consider charge placement. Less electronegative gets positive, more electronegative gets negative. But first, before I care about where the charge is, I want to make sure that every atom has a maximum octet. This is the major resonance form, which is why, I erased my little energy diagram, which is why the intermediate is lower in energy relative to just benzene reacting. This oxygen is stabilizing the resonance, lowering the energy of the intermediate, lowering the energy of the activation barrier. I'm going to say this. The orthopara directing and the activating, it's the same thing. It's this. What's my last step? Elimination, which means I'm going to have to break a carbon-hydrogen bond. I'm going to have to reform my catalyst. So I'm going to have to break a chlorine aluminum bond as well. The AlCl bond is taken by chlorine and attacks the hydrogen. The CH bond. Now, this is another fun part about resonance. All of these arrows that we did when the oxygen forced the paracarbon to attack, now all of those arrows go back. CH forms a pi bond. The pi bond adjacent to it shifts over. The CO double bond breaks back to the oxygen. And if you pay attention, that means aromaticity is reformed. Yay. Thank you. And for Sarah, HCl, AlCl3 reform. That was you that said that earlier, right? Let's take a break, shall we? Holy. Five minutes.
You can only go like one arrow at a time, right? Like you can't skip.
Your arrows can only go one atom at a time.
No. Like, you know how the arrow goes from the hydrogen, like you go one step at a time.
I mean, technically, these are all happening at the same instance. So we're not showing A, then B, then C. But it is helpful to think about how it propagates. Because the chlorine takes the hydrogen, these electrons are freed up. Where are those electrons going to go? Carbon will use them to form a double bond. That will break the octet at this carbon, so its double bond shifts over. That will break the octet at this carbon, so its double bond shifts over. There is another way to think of it, though. I like to think of it as propagating this way. But oxygen is electronegative. It's like always asking for its electrons back. Oxygen put its electrons on loan. Now it wants its loan back. So oxygen is pulling electrons back, which means that these electrons are getting pulled in that direction, which means that these electrons are getting pulled on even tighter. That makes this a very acidic hydrogen, which draws in the chlorine to come and take it. You can actually think of it as a push or a pull. It's both. And it's happening instantaneously. But here's what's happening. This happens, then something forms, then this happens, something forms, then this happens. So this is a three-step mechanism. You could get 3 snapshots of things happening as these molecules run into each other. Good question. Lily.
I'm still confused on the positions with this.
Mm-hmm.
Like, how did I know from here, like where you put that guy?
Mm-hmm. Well, there are 2 groups on the ring. Both are bromines.
Yes.
Bromines, as halogens, will tell the ring to direct itself for the next substituent to attack ortho or para.
Okay. Which would be
So this bromine, where is ortho?
here
Good. And?
and here.
Yeah. Where's para?
Here.
Oh, it's already taken.
Oh, okay. So just because of the halogen is how we knew that.
Well, and then this halogen too. Where's its ortho?
Here
Yeah.
and here.
Yeah.
And
And
then
its para is taken.
Okay.
So it actually wouldn't have mattered which position you went to.
Because, okay.
It's symmetric. It would have been
So,
the
For
same
one
exact
bromine.
molecule no matter what.
okay.
But either bromine would have done it, and all 4 positions are exactly the same.
Okay.
Mm-hmm.
Thank you. That makes more sense.
Good. Now this one's harder
Yeah.
because these are not the same group,
No.
but we rank the directing effect by the activating effect.
Okay.
These are both deactivators, but bromine is less of a deactivator than sulfonyl.
Yes.
So in theory, it's more of an activator.
I think ranking it like this was helpful.
Thank you. I did try for that.
That was helpful.
Good.
So then with the bromine, since it's a halogen,
Yep.
then it's back to this.
Yep.
Or para.
Orthopara.
Yeah, okay,
Yep.
thank
The
you.
sulfonyl would have said go meta.
Yes.
And by going meta, the sulfonyl would have said, can you also go very high energy, please?
And we don't want that.
And the bromine, it's not even that we don't want that. We might want that.
Okay,
But what are you more likely to get?
the less energy one.
Yeah, it's more likely your molecule will fall through a lower energy route.
Okay.
Yeah,
Thank you. I
you're
have one
welcome.
question.
Yeah, yeah.
So, I'm just like messing up my charges. So anytime you get a lone pair, that causes a positive charge?
Well, it actually stays neutral.
Okay, so this is us just telling us that the whole molecule is neutral.
That's true, yep.
Okay,
But the bromine has a formal positive charge and the iron has a formal negative charge.
and is that just because of like our sticks and dots valence electrons?
Yes, it is.
Okay,
That's it.
okay.
But you can also think of it like this. Here, bromine is neutral. Now, make it share an electron. I don't want to share an electron. Right, so now it's positively charged.
Oh, okay.
It has less electrons for itself compared to when it did before. Less electrons for itself, positive.
Okay.
Iron, on the other hand, now has more electrons than it did. More electrons for itself, negative.
Okay, thank you.
You're welcome. Okay, do you want to go through the mechanisms on here, or do you want to go through the mechanisms on the homework?
Can we go through the last problem on the homework?
Yeah?
But are we gonna have to know these for the unit test this week?
Yeah. Well, I'm asking you to know 4 mechanisms: bromination, chlorination, acylation, alkylation.
Okay.
So you have all of that. Huh?
Oh, sorry, I was saying for like active or for like the written.
I don't have you guys do arrow pushing on active.
Yeah, but I feel like you need to know the arrow pushing to like do the last one.
Oh, maybe.
If you do the written one, then I'd gladly take that.
Yeah?
Or you could do both.
Here's what I'll say. On this worksheet, the third reaction that we have is alkylation, correct? And I want to point out the reagent that you're given against the product that you get. Didn't I say earlier when you guys were solving that problem that added a methyl group to phenol, that you just take the group you want and slap Cl on it, and now that group is attached to your ring? Do those look like the same group? Wouldn't you think like that's the aromatic ring and that's the group I should get? What's happening? Chemistry. People have thought chemistry was magic, alchemy. How come these aren't the same group? Carbocation rearrangement. Remember I said that you, when I gave you that reaction diagram of all 6 EAS reactions, I said you can do the reaction with AlCl3, or you could have an alkene with H+. Both reactions have a carbocation intermediate, and carbocations will reform to give you the most stable carbocation. So this reaction goes through a carbocation intermediate. So I'm going to give you this one actually, but what I'll do is give you the just the first step, the activation step of the electrophile, because the rest of it is very much similar. In the activation of the electrophile, okay, we've got benzene, it's not going to do anything. Chlorine, just like last time, attacks aluminum. I'm going to call this next step 1A, because we actually haven't activated the electrophile completely. We are still in the process of getting the electrophile that this structure wants. Aromatic ring, still present, still doing nothing. In fact, we could name A1 carbocation formation. The chlorine here, okay, actually let's look back at our chlorination. After we formed this complex, chlorine to aluminum, nothing else happened. We attacked the electrophile. We've got something very similar, but it's not chlorine to chlorine anymore, it's carbon to chlorine. And now the chlorine takes its electrons away and leaves us with a carbocation. And benzene is doing nothing. So alkylation mechanisms, by default, are one step longer than chlorination, because we have to do this extra formation of the carbocation step. And anytime we have the formation of a carbocation, we have to be wary of a carbocation rearrangement. Do you know why I list this out for you guys? Because I don't want you to guess later on. I don't want you to sit down and look at a reaction to practice and wonder, what steps should I do? I'm telling you how many steps I want to see. In this case, my carbocation rearrangement is incredibly fast because primary carbocations are not stable at all, but tertiary carbocations are very stable. Primary carbocation, hydrogen shifts over, leaving in its wake a tertiary carbocation. Now what? Nucleophilic attack, elimination. What will the elimination look like? Exactly the same. AlCl4 breaks an aluminum chlorine bond to take the hydrogen to reform the aromatic ring. So after this, step 2, step 3, you get your product. But let's move on. Ella.
I don't understand where the positive charge goes.
Positive charges don't go anywhere.
Well, but when there's not a positive charge on the product, like up at the top.
Well, there weren't positive charges on the starting materials.
I know, but I don't.
Where did the positive charge come from? This is not a bad question, by the way. Where did the positive charge come from? So chlorine had 3 lone pairs. It shared a lone pair, so it has less electrons for itself. What happens when you have less electrons? You take on a positive charge. That chlorine, before in chlorination, it couldn't take its electrons from the chlorine. Oh, but chlorine can take electrons from carbon. So what happens when carbon loses its bond? Now it is short electrons. So the positive charge ends up on carbon because chlorine started giving electrons to aluminum. And that's where the balance is. It's not like a positive charge just formed out of thin air. That positive charge is balanced by a negative charge.
I just don't get how it goes away if it's on, if it's tertiary.
Yeah. Where did the positive charge go last time? It went onto the ring. This positive charge on carbon is an availability for the ring to attack. So the ring bonds to that carbocation. Now that carbon has...
Oh, and then the H, and then it does resonance, and then it kicks on. Okay.
Good.
Thank you.
Now that carbon has a fourth bond. Now the positive charge is on the ring. Now it's in resonance, just like this. And then the chlorine takes off the hydrogen.
Thank you.
Good. I do worry about skipping those steps, but you've seen the nucleophilic attack and the elimination twice. That's not different here. The only thing different here is the formation of the electrophile. All right, well, that sucks actually, because that on your written work you have alkylation or bromination, so I don't actually have an acylation one for you to do on your homework, so I'm going to have to just give you guys the last one. Acylation is actually quite similar to alkylation. I also want to point out something. I updated the homework again. Sorry. In this update, I added a line that says you need only show, which is not to say you must only show. It's just to say you need only show. This is limiting the amount of work you need to do. The most major resonance forms. I just erased it, but we had one major resonance form. I'm going to give you a hint in that this bromination reaction on the written work has two major resonance forms. The oxygen and the oxygen that are ortho and para to the new group, they both stabilize the resonance. Those are the major resonance forms I want to see. Do you remember that I set the number of points based on the steps? Well, alkylation has more steps because of that carbocation formation than bromination. So bromination has an extra resonance form. Now they have the same number of steps. You'll be showing the same number of intermediate steps. Can you guys tell me that alkyl group in that first reaction? Orthopara director? Or no? Yeah, the alkylation on your written work. Orthopara director? The isopropyl group? It is. Why is it an orthopara director? It's because there's a resonance form where the positive charge is tertiary. What's more stable, a tertiary carbocation or a secondary carbocation? Tertiary. That's why alkyl groups are orthopara directors. They can hold on to that tertiary carbocation, stabilize the intermediate even more. Okay, I want to show you guys acylation. We're going to do the one that's from the sheet, which means I have bromine attached. Is that right? And bromine, of course, is what type of director? Orthopara. Step one, activation of the electrophile. I'm going to abbreviate bromobenzene since it's not going to do anything here. I'm going to abbreviate it as PHBr because that's bromobenzene, phenyl bromide. Can you guess what happens in this step? Beautiful. Chlorine bonds to the aluminum. Nothing new. Well, I guess the only thing new is that it's a new group. It's not a chlorine molecule and it's not an alkyl chloride. This functional group is what? a weird one. Acid chloride. It's like a carboxylic acid, but with a chloride instead. Just like alkylation, this is going to have a 1A, but it will not have a 1B. It is another carbocation formation. This carbocation has a more technical name because of its relationship to the carbonyl. But I always forget its more technical name, so I apologize. Here's the deal. There are two ways that you can show this, but I would like you to show the most stable resonance form. There are two resonance forms of the intermediate that comes next, the most stable of which is when oxygen donates electrons to the carbonyl carbon. I know, it's weird, right? Because now that carbon's going to have to kick something off, so it kicks off the chlorine. Which means that now that carbon and that oxygen are triple bonded to each other. And the oxygen holds the positive charge. This is the alternative resonance form. So can you tell me why the triple bonded positive oxygen is more stable? Octet rule. Broken octet on carbocation, full octet with the oxygen ion. So it's not a carbocation in both of its forms, but it is essentially a carbocation. By the way, this structure here, I know a lot of students draw it like this, because it looks like the carbonyl, but now there's just a positive charge. That's technically wrong. Why? Because that carbon has 2 electron regions. That's a linear sp atom. So it looks like this. Those 2 regions are as far away as possible. Step 2, nucleophilic attack. All right, now I get to draw out my aromatic ring, and I get to show all of its pi bonds. Does it matter which carbon of the ring attacks? Yeah, it does. It needs to be the carbon para to the bromine. So this carbon needs to attack. My arrow will come from its pi bond. And it will attack the carbon, which breaks open the triple bond to oxygen. Oxygen was loaning its electrons. Now it wants its electrons back. But do you remember that I said I want you to show the major resonance form? The resonance form that forms here is a positive charge on carbon, no octet. So this pi bond shifts over, and bromine shares electrons, just like oxygen does, just like nitrogen does. This is a structure that earlier in the semester, Milena described as cursed. Now you understand why it exists. Full octets in this resonance form, which means more stable. Why is bromine an orthopara director? It can stabilize the resonance form if the group is orthopara. Step 3, elimination. Oh, do you know what I didn't do? I didn't show that aryl hydrogen that needs to get eliminated. And I like to show that every time so I don't forget it. So I'm drawing it in so that you copy it down so that you don't forget it too. How do you think the elimination is going to take place? Same as always. Chlorine takes the bond from aluminum, attacks the hydrogen. CH bond forms a pi bond shifts over, bromine takes its pi bond back. Fun? It's very repetitive, isn't it? We saw the same thing over and over and over. What I have tried to give you in these examples is a combination of the reagents, bromination, chlorination, alkylation, acylation, as well as a combination of the groups that can help stabilize. Yeah, Katie?
Is the molecular reactant supposed to be AlCl3 or is it there are 5?
No.
Okay.
AlCl3, thank you, not AlCl4. That's another thing that helps if you draw out all of those chlorines, because you typically won't draw more chlorines than you need. All right, so I want to point out something about your written work. If you do the first EAS mechanism, then you should be drawing a major resonance form that looks like this. I've abbreviated that cyclopentyl ring as CP, but you're looking for that tertiary carbocation. That's the resonance form I want to see. If you're doing your second mechanism, then you should have both a positive charge on one oxygen and a positive charge on the other oxygen. This one is the only one I'm going to ask you to show two resonance forms for. You are allowed to show all resonance forms. So take yourself through that process if it's helpful for you. But what I'm trying to explore is demonstrating that these groups stabilize the formation of that resonance in the first place. So you don't need to show all resonance forms so long as you can get to that major resonance form. It's a gamble. I'll see how your homework goes tomorrow or over the weekend. All right, we have just enough time to look at the bottom page here and talk about some of the examples of your synthesis. Multi-step syntheses are assigned points based on the number of intermediates and reagents that you have to show. These are two-step intermediates. That means step 1 reagent, intermediate, step 2 reagent, final product. Yeah? 3 points. Step 1 reagent, step 2 reagent, and the intermediate. The second set are 3-step mechanisms, which is 5 points. There's an extra step and an extra intermediate, 2 points extra. On the two-step reactions, on the two-step syntheses, those are both EAS only. But on the 3-step, you will need to use something from the benzylic reactions. You don't actually need to do any NAS, although it wouldn't have been hard to put NAS on there. But you will need to include a step from the benzylic reactions in section 15. Do you guys remember the benzylic reactions? Like benzylic halogenation, oxidation, reduction. Okay. Do you guys want to talk about any of these problems? Should we look at one of them? Which one? Number 4, so like bottom right. Things that I need you to pay attention to in these multi-step syntheses are the directing effects. How are the groups oriented next to each other? How can I get them to that orientation? So can someone tell me on that bottom right reaction, is it okay if I erase this? What is the substitution of my 2 final products, on my 2 substituents? Sorry? How are the 2 substituents oriented? Meta to each other. Okay, which of them is a meta director? How do I orient 2 groups meta to each other if I have no meta director? Can't. So where's the meta director? Also, how do I get that group? Alkylation? Well, we said earlier, if I want to predict alkylation, then I just need to have this group connected to a halogen, right? By golly, didn't we just do that earlier? Isn't it on your mechanisms page? And that does not give that substituent. What does it give? Tert-butyl, because of a hydride shift. There's a carbocation rearrangement. I can't make that group by alkylation. There must have been something else that made that group, and then it transformed into that group. There must have been something else that added those carbons, and then it transformed into that group. Do you see what it is? A what? NAS? Not NAS, because we haven't seen how to attack with a carbon. What about reactions from our benzylic chapter? Here's what I'm going to say. First of all, this is 3 steps. So I know I've got step 1, intermediate 1, step 2, intermediate 2, step 3, and I have my final product. Benzylic oxidation gives me a carboxylic acid. But I don't have a carboxylic acid. Tert-butoxide.
Oh, I have the tert-butoxide.
Okay, let me ask a different question. This is all that brainstorming. I know I can't do simple alkylation, so I'm going to have to do something else to get those carbon groups onto the ring, and then I'll have to change that something else so that it looks like this. But what about the chlorine? Could the chlorine go first? No, because it's an orthopara director. So whatever does this, chlorine will put it ortho or para to itself. Yeah? Hydrazine reduction. What does hydrazine reduction do? It takes a what group to an alkane? A carbonyl. A carbonyl? What kind of director is a carbonyl? Meta director. So if I do acylation, then I can get a carbonyl onto my ring, with whatever R group I want. Now I have a meta director. Now I can direct my chlorine meta to my carbonyl. And then I can hide the fact that there was ever a carbonyl there by doing hydrazine reduction. If you give this to me, I will take points off. Why? You're not showing me reagents, and you're not showing me the intermediate. I want the reagents, I want the intermediate, but this is the biggest hint that I can give you. Amen? Section 15. It's one of our benzylic reduction reactions. You could also do, it's called Wolff-Kishner instead of hydrazine, but if you know what hydrazine is, then you'll know how to do it. Thank you. Oh, I want to point out one other thing. What if I wanted to go from benzene to something like this? I've got para-methylphenol. How do I put OH onto a ring? Alkylation does not put OH. Alkylation will do this. Sulfonation is different. Nitration is different. How do I put OH? NAS. This is a 3-step mechanism as well. This is brominate, substitute the bromine for OH, NAS, and then put the methyl group on. I see a lot of very creative use of reagents on these syntheses. Don't get creative. Look for the things that we've already done. How do I put a specific functional group on? Look for the reactions that build that functional group. You guys are going to do great. Go study. Have a great unit test doing a synthesis and a mechanism. That's correct. It's open until Monday because we'll have class again on Tuesday. Yeah. This one, BR2, FeBr3, and then NaOH, and then alkylation. How do you get OH on? Good night, Indigo. You can't do acylation, alkylation, nitration, sulfonation, bromination, chlorination. None of those are OH, right? This is how you put OH on. You first need a bromine or a chlorine on the ring. And how do you know that, Peyton? Look at your homework. Substitute for nitrogen, substitute for oxygen. You've been seeing how to put those on. So that's not new. Just identify your group and find reactions that put that group on. Don't look so sad. You're going to do great. You're going to feel so smart after this. Hi. Yeah, absolutely. Yep. And you can resubmit and resubmit and resubmit and resubmit. You can get full points on this. I want you guys to get full points. I'll send out a message, by the way. Everybody's gone. Yoon pointed out a mistake I had earlier, and I updated it this afternoon.
Wait, even the first one?
Yeah, even the first one, because it was something with this one down here. I showed the wrong thing being substituted. I'll send out a message to remind you guys. Thank you. Have a good night. Have a good weekend.
I have a question.
Yes.